To begin our project, we started with a deep dive into the raw loan dataset using a comprehensive diagnostic script. We were working with a training set of 36,000 observations, and right away we noticed a significant hurdle in the data distribution. Only about 22% of the applicants in our training set were labeled as default, and in the world of machine learning, this class imbalance is a major red flag because it means the model can look very accurate on the surface just by being lazy and predicting that no one will ever default. Since our goal was to maximize the F1 score, we knew accuracy alone would be a misleading metric.
Exactly. And as we can see here, we look at the numeric diagnosis on the screen. They can give us more to think about, really. When we looked at the income column, the skewness was extremely high at around 36.16. We had applicants making $8,000 a year and others making over 7 million. And that kind of range can really confuse the standard model. So we also flagged the impossible data, as they call, like a maximum age of like 144 and employment experience of 125 years. And we use these insights to really cap the age at 95 and experience at 50 and applied log transformations to the income to really stabilize that distribution. And we also noted that categorical features like education had very low cardinality, so one hot encoding was our most efficient strategy.
For our first approach, we developed a logistic regression baseline. And as you can see here in the first learning curve, our baseline shows both the training and validation lines plateauing very early at relatively low F1 scores. This was our clear indicator of high bias. The model simply was not complex enough to learn the underlying patterns.
So this model gave us our first baseline. While logistic regression is fast, I think its main weakness really was its inability to find the nonlinear breaking points where, for instance, a borrower suddenly becomes a high risk. And after seeing this clear underfitting, our next step was to transition to a more complex and nonlinear model, the hist gradient boosting classifier. And so this out of the box approach gave us our first real Kaggle submission of 0.817.
That .817 score motivated our second model iteration, which was our best performer. We moved beyond raw columns to engineer features with financial logic, work start age to gauge maturity, and expected interest to measure the true dollar value burden of the debt.
So when we look at the feature importance plot on the screen right now, you can see that our engineered features, so all of these features, as you can see in the top, are the top predictors. So this really justifies the time we spent on domain-specific engineering.
Moving to the second learning curve, this represents our optimized his gradient boosting model. This, you'll notice the lines converge tightly at a high F1 score, and quantitatively, our training F1 was 0.852 and our validation F1 was 0.849. This generalization gap of only 0.3% provides the rigor needed to classify this model as well fitted.
And we also verified the stability as well of this model. So our standard deviation here across the five-fold cross-validation was at 0.004. So this low variance really proves that the model is robust and not sensitive to specific data splits. To achieve this, we tune hyperparameters like the max depth to 8 and use an L2 regularization of 2.5 to really prevent the trees from memorizing noise. We also optimize our decision threshold to 0.38, balancing precision and recall perfectly to hit our peak score of 0.849. And finally, looking at the third learning curve here for our ensemble experiment. So we really tried a rather complex soft voting ensemble, but it dropped our score down to 0.837.
While the training score remained high, the validation score struggled to keep up, and the gap between the two widened significantly compared to Model 2. This visual evidence of overfitting is exactly why we reverted to our second model. It taught us that our optimized single model generalized better than an over-engineered ensemble.
So, from a business perspective, the confusion matrix really helps us understand the financial trade-offs, right? In lending, a false negative, missing a defaulter is far more costly than a false positive, or denying a good borrower. So, really, by adjusting our threshold to 0.38, we prioritize protecting the bank's capital.
We also interpreted the precision recall curve. It allows us to see exactly how much precision we're sacrificing to gain recall. By finding the elbow or sweet spot on this curve, we maximize the practical value of the model for a real world banking scenario.
So, if we had more time, we'd look for external macroeconomic data like regional unemployment rates to provide broader context.
Finally, for production, we'd implement a monitoring strategy to detect data drift. If an applicant's income or interest rates drift significantly from our training baseline, it would trigger an automated alert to retrain. This ensures our classifier remains a reliable decision-making tool long after this hackathon ends.